Welcome to Easy Academic. Today we will be talking about lines in 3D as part of our Introduction to Linear Algebra series. In this video we will be going over parametric and symmetric forms of representing lines in 3 dimensions. To start, we will go over parametric forms. So parametric forms of representing lines in 3 dimensions require us to represent the x, y, and z dimension in terms of a new variable. Most often we call this new variable t. So if we were to represent a line in 3 dimensions, we would denote it as r of t. This is a line function with respect to the variable t. And we set that equal to r naught, which is an initial position variable, or vector rather, that tells us the offset from the origin, plus our parameter t times some vector v, which represents information about the direction of the line. And so since this is a parametric equation, we can represent r in terms of its x, y, and z components. So r of t can be broken down into x of t, which is equal to x naught plus some arbitrary value, let's call it a, times t, where a is the first entry of v, y, which is equal to y naught plus b times t, where b is the y value in the direction vector, and z, which is equal to z naught plus c times t. So based on this, we would be given a vector v, or would be asked to find the vector v, such that v is equal to a, b, c. Oftentimes when representing lines parametrically, you might see a different notation for vectors. Vectors might be notated using these brackets, and each entry being separated by a comma. So if you see this notation for a vector, know that it represents the same information as this vector. We will now be going over symmetric forms. So the symmetric form of a line equates x with respect to a, y with respect to b, and z with respect to c in order to represent a line. So to clarify this, we use this general expression. So here we have the general expression x minus x naught over a equals y minus y naught over b equals z minus z naught over c. This is fairly simple to remember, as all you need to do is remember that you subtract your value for x from your given origin offset for x, and then divide by your corresponding value from your direction vector. The symmetric form can be derived from the parametric form if we equate all values of t. So in order to do this, let's rewrite out the parametric form and show you how you can obtain the symmetric form in case you aren't able to memorize this expression. So if we have x equals x naught plus a times t, we can rewrite this by subtracting x naught from both sides, which will give us x minus x naught equals a times t. We can then divide a from both sides. So this will give us x minus x naught over a equals t. As we can see, this is one part of the expression in the entire symmetric representation. Doing the same for y and z would give us y minus y naught over b is equal to t, and z minus z naught over c is equal to t. And we know that since all three of these are equal to t, that means they are all equal to one another. And so that's another way that you can derive the symmetric form. Let's now take a numerical example. So say we are given a point, r naught, which is our initial offset from the origin. And let's say that this point is equal to 1, 2, -1. And let's say that we're given a vector which represents our direction, v, which is equal to 3, -2, 4. Let's first represent this parametrically. So parametrically, we get that x is equal to 1 plus 3 times t. So we got 1 from here and 3 from here, and we multiplied by t. We get that y is equal to 2 from here, minus, because we have a minus here, 2 times t. So we get the minus from this second entry in the direction vector. And we get that z is equal to -1 from here, plus 4 from here, times t. So this is how we can represent a line parametrically. Symmetrically, we can either convert this or we can use our general expression. So let's use our general expression to show the relationship in terms of equating all of the sides to t. So again, we can see from our general expression that x minus x naught over a equals y minus y naught over b equals z minus z naught over c. So what we'll do is we'll write this as x minus 1, which is the first x value in r naught, over a, which is 3, equals y minus 2, which is the second value in r naught, over -2, equals z plus 1. And take note that since this is a negative value, as the third entry into r naught, if we do minus a negative value, we add. So we have z plus 1 over 4. And this is how we represent our value symmetrically. If you'd like some practice, you could attempt to do you can attempt to represent the following point and direction vector symmetrically, just for some practice for the viewer. So let's say we have the point r naught equals 0, 1, 5, and we'll have the direction vector v equal to -2, 1, 3. So you can pause the video before I reveal the answer. So symmetrically, the representation of the answer is x minus 0 over -2, which we got from here, equals y minus 1 over 1 equals z minus 5 over 3. So if you found this video helpful, please be sure to like the video and subscribe to the channel for more useful educational content, as well as feel free to share this video with whoever you think might find it helpful as well. If you have any questions, be sure to leave them in the comments below.